Well, hi guys. I just thought I would step in here and give you a brief talk about a way of thinking about compactness that involves closed sets instead of open sets. So recall the definition of a compact topological space. It's just one for which every open cover of X has a finite subcover. So that, of course, is a description that is based on open sets, because an open cover, it consists of a collection of open sets. So it might be natural to wonder, is it possible to describe compactness using closed sets instead? Turns out the answer is yes. And in order to tell you what that description is, or what that characterization is, I'm going to introduce something called the finite intersection property. Okay? So I've put it on the board here as a definition. A collection of sets script F has the finite intersection property if, whenever you intersect finitely many of them, the result is non-empty. Okay? So if you take 7 sets out of script F and intersect them together, it's non-empty. Or 12 sets, it's non-empty. So this is a property that applies to a collection of sets, and it may or may not be true, right? But if that collection of sets has this property that all intersections of finite numbers of elements of that set, of the sets in the script F, is non-empty, if that property is true, then F has what we're going to call the finite intersection property. And it turns out that I can describe compactness for you using the finite intersection property applied to a collection of sets. And it turns out that those sets that we're going to look at are going to be closed sets. So with that in mind, let me come over here and state a result. This is proposition 8 from chapter 7 of Gemignani's topology book, Elementary Topology. And it just says the following: X is compact if and only if, so we're going to have a way of describing compactness here, given any family, I'll call it the set of F sub I, where I is in capital I, some index set, given any family of closed, these are now closed, subsets of X with the finite intersection property. Okay? Here's the finite intersection property. Okay, so if we have a family of closed sets, take any family of closed sets with the property that all finite intersections are non-empty. Okay? Then, when you intersect all of the sets, okay? So this could be an infinite number of closed subsets of X, right? We are given that finite intersections of finitely many of the sets, are non-empty. But what compactness is equivalent to, is that any collection of closed sets with the finite intersection property actually has the property that when you intersect all of those sets together, the result is non-empty. Okay? So I'm going to do the proof in both directions. This is an if and only if. I'm going to do the proof. Of course, compactness as a definition involves open sets. But we know how to kind of go between open sets and closed sets, of course. We just use complements, right? So I can very easily kind of transition from one to the other. So that's how this proof is going to work. Let's do the forward direction first. Let's assume that X is compact. All right, we'll assume that every open cover has a finite subcover. And I'm going to take a family of closed subsets of X. Okay, so let the set of F sub I, where I is in capital I, be a collection of closed sets. Okay, I have to prove that given any such collection of closed sets, these are subsets of X, of course. Sorry, subsets of X. So you take a collection of closed subsets of X. Well, if they have the finite intersection property, then the intersection of all of them has to be non-empty. I'm actually going to prove that by contrapositive. In other words, I'm going to assume that when I intersect all of the sets, that the result is actually empty. Okay? I'm going to assume that this intersection is empty, and I'm going to show that I can actually get finitely many of the sets to have an empty intersection. Okay, so it's just the contrapositive of this statement. In other words, if this is the case, if we assume that all of the sets intersect trivially, then I'm going to show that basically the collection of closed sets does not have the finite intersection property. In other words, we can find a finite number of these FIs whose intersection is already empty. How are we going to do that? Well, so what we're going to do is we're going to let U sub I be equal to X minus F sub I, which is open. So this is exactly what I was talking about a moment ago. The complement of the closed set Fi will be an open set. I'm going to call that U sub I. Okay. So then if we take a look at X, okay, of course I can write X as X minus the empty set, but that's just X minus the intersection of the F sub I's, and that is the same thing as the union of X minus F sub I, which is, in other words, just the union of the U sub I's right here. Okay? And so, what do we have? We actually have an open cover of X. These U sub I's are an open cover for X, and if we are assuming that X is compact, well, then that open cover has to have a finite subcover. Okay, so let me come back. I'm going to erase here. If you need to pause or rewind the video to remind yourself what these definitions are, by all means go right ahead. I'll try to keep the proposition stated down here so we can keep referring to it. But anyway, so since X is compact, the set of U sub I's, where I is in the index set I, has a finite subcover. Okay, and so let's just say that X can be written as U sub I1 union U sub I2 up to U sub IK. Let's just say that we can do that. Okay. Well, then what I'm going to do is I'm going to, of course, go back to the corresponding closed sets, Fi1, Fi2, and so on, and I'm going to see if their intersection is empty. Okay? So then, in other words, if I look at F sub I1 intersect F sub I2 and so on, this is a finite intersection. Okay? So let's just take a look at what this actually gives me, right? So this is going to give me, X minus UI1 intersected with X minus UI2 intersected and so on up to X minus U sub IK. And that can be written as X minus the union of these sets using the usual De Morgan's law, right? But the union of all of those sets is exactly x. So it's empty. So here we have an intersection of a finite number of the sets in my family of closed sets that is empty. That means that the finite intersection property fails. So in other words, if all of the sets, this was the assumption, if all of the sets have a trivial intersection, well, then we can actually construct a finite intersection of those sets that's also empty. So that proves the forward direction, right? That finishes the proof. Kind of basically by contrapositive, okay? All right, I'm going to go ahead and erase. Actually, I'm just going to erase everything except the proposition, and we're going to prove the backwards direction. We're going to prove that if the finite intersection property holds, implies that the intersection of all of the sets is empty, then, based on that, X is compact, right? So, for the backwards direction now. The backwards direction, okay? So, to prove that, here's X right here, so to prove that X is compact, I'm going to prove this, I have to start with an arbitrary open cover. So let's let the set of u sub I, where I is in some index set, be an open cover of X. Okay? Our job is to produce a finite subcover. So what we know is that if we take the union of all of the u sub i's, I'm going to get the whole set X. Okay? This is what we know right here. All right. So what I'm going to do is I'm going to take this time I'm starting with the open sets. I'm just going to take their complements and let f sub I be x minus u sub I, which is closed for each I. Right? So each of these fi's is closed. That's creating for me a family of closed subsets of X, right? So we have a family of closed sets. Now let's look at, so this is our assumption. Let's look at the intersection of all of these f sub i's, okay? So then if we take the intersection of all of the f sub i's in this collection, that's really just the intersection of x minus u sub I. And that's just the intersection, well, actually what I want to do there is rewrite that as x minus the union of the u sub i's. But the union of the u sub i's is equal to x. So this is empty. This is empty now. Okay, so I created a family of closed sets where the intersection of all of them is empty. So if we're assuming this right-hand side of this biconditional, then that must mean that if the intersection of all of them is empty, that this family does not have the finite intersection property. So by assumption, the set of f sub I, right, does not have the finite intersection property, which I've erased, of course. But what it means then is that some finite number of these capital F sub i's will have a trivial intersection. So there exist f sub I1, f sub I2, and so on up to f sub ik with the intersection of these guys empty, right? If the finite intersection property fails, it means that you can find finitely many of the sets to intersect, and it's already empty. Right. Okay. Well, now if I then take a look at the union of the corresponding use of i's, I claim that just this finite collection here is going to cover X. Remember what we're trying to prove. Starting with this open cover of X, we're trying to come up with a finite subcover. This is going to be it, right? This union is going to equal X. Let's just check it. Okay, this is all we have left to do. So we just have what? X minus Fi1 union X minus Fi2 union ... and so on. Right? And then that can be rewritten, yeah, that can be rewritten as X minus the intersection of Fi1 all the way up to Fik. But that intersection was empty. So I just get X. Okay. So we have a finite subcover. We have a finite subcover in that case. Okay? So this is a proposition, again, just to summarize. It describes compactness in terms of closed sets. So instead of every open cover has a finite subcover, what this is saying is that every collection of closed subsets that has the finite intersection property must have a non-empty intersection when I do the intersection of all of the sets. Okay? So just another way of thinking about compactness in terms of the closed sets. I hope that this finite intersection property description of compactness makes sense to you. As always, I'm available to answer questions and to help out, but hopefully this will get you started. And thank you guys very much for watching, and hope you have a good rest of your day.